If we have a long wire with a uniform charge density that we're going to call lambda, that's the charge per unit length in coulombs per centimeter, coulombs per meter, microcoulombs per kilometer, whatever. If we have a long charged wire with charge density lambda, then symmetry arguments will show us that the flux through any cylinder of length L and radius R, whose axis coincides with the wire, is going to be 2 pi kq, where q is lambda times L. The charge inside the cylinder, that is, over distance L at lambda being charged per unit length, has to be lambda times L. This is just a repeat of the calculation we did before, but this time we're using symbols. Before we multiplied the 10 centimeter length by the 7 microcoulomb per centimeter charge. Here we just designate that lambda times L. Then the flux is 4 pi kq, which is 4 pi k lambda L. The area of the cylinder is 2 pi r, the circumference of its cross-section, times its length L. We could unroll this cylinder into a rectangle of length 2 pi r and width L. Now let's look at the symmetry argument that shows us that the flux has to be uniformly distributed over this area and everywhere perpendicular to the curved surface of the cylinder. Okay, here we see an end view of the cylinder. Okay, let's look at this one first. Okay, if at every point the field has the same direction, except for one point where it isn't in the same direction, then we don't have symmetry, because by rotating this thing a little bit, the point where the field is in a different in a different direction than all the others is going to change. Okay, rotating the wire about an end, rotating like this, can't have any effect on the electric field at any point. So that if the point of non-symmetry is here, that point of non-symmetry can't move over here simply by rotating the wire. It follows that since rotating the wire is equivalent to rotating all of space, since this point would have to rotate around to here, and the electric field would have to be out of kilter at this point rather than this point, that this can't happen. We can't have a point where the field has a different direction. That would contradict our ideas of symmetry of space, our experience of symmetry, and our assumption of symmetry. Similarly, if the field is always in the same direction, but that direction is not radial, that is, it's always tilted a little ways away from radial, all in the same direction, because by this argument they all have to make the same direction with radial, then rotating this thing wouldn't have any effect. The field would still always be the same all the way around at any point. The field at this point wouldn't be affected by rotating this point around to here because of the symmetry of the situation. However, we also have end over end symmetry, and if we switch the ends of the wire, that's going to switch the directions of these vectors. And therefore, we can't have either of these situations, because when we switch the wire end over end, that can't make a difference in the way the electric field looks. And in this case, it certainly would. So the symmetry argument shows that the vectors all have to be the same. They all have to have the same length and the same direction. And that direction has to be radial by the end over end flipping. And let me mention, this vector differed in direction from the rest. If one vector differed in length from the rest, then we'd make the same argument, just rotate it, and that point where the vector is shorter would move to a different point, and that can't happen. The end over end symmetry also shows us that if we had a point where the field wasn't perpendicular to the wire, what would happen if we rotated the ends of this wire? Well, this thing, instead of being tilted off to the left, would be tilted off to the right. and it wouldn't make, that would violate our symmetry also. Instead of having a point where the field is off to the left, we could rotate it around this point and we'd have the field off to the right, and there can't be a difference. The rotation, the switching of the ends can't make a difference. If we switch the ends, leaving this point the same, that would change the tilt. As we switch the ends, the tilt would go from here to here. Switching the ends can't make a difference. And if the field was like this, switching the ends would indeed make a difference. Okay, so going back to the situation here, we've determined that the charge inside the cylinder is lambda L, the flux is therefore 4 pi K lambda L, and the area is 2 pi RL. The flux has to be 4 pi RL, but the flux of an electric field E perpendicular to the surface of this thing and everywhere uniform will be E times the area 2 pi RL. We solve this for the electric field. E is going to be this over this. We see that the pi's cancel out. 2 divides 4 2 times. We have K lambda over R. The striking thing about this is, remember that a point charge falls off inversely as a square of distance. The electric field in this case just falls off as the distance. This is because, of course, we have the field distributed over this long wire, and it's because of the cylindrical symmetry of the situation. Whereas with a point charge we had a spherical symmetry, with a long line charge, straight line charge, we have a cylindrical symmetry. And the cylindrical symmetry gives us this inverse R relationship just because of the relationship between distance from the axis and area of the cylinder. Okay? The area in the for a sphere would have been 4 pi R squared. Being a cylinder, it's just a 2 pi R. First power here, second power there.